Hello and welcome to my new video. In the coming weeks, I will explore how to model chemical structures using script-based modeling, and Fullerenes will be my first examples. Why using script-based modeling when there are sufficient dedicated software tools available? First, programs like Pov-Ray will give you a much higher degree of creative freedom when it comes to how you want to visualize your molecule. Second thing is that there are some structures, highly regular ones of course, which can be better and more easily modeled by script-based modeling when compared to chemical modeling software. Graphene and graphite are examples for this. Fullerenes are somewhat more complex, but they are still doable, as you will see. The sources I've been using for producing this model can be found in the comment section to this video. You can also find there a link to my GitHub account where I will put a copy of the Pov-Ray script I've been using for these Fullerenes. Building blocks of Fullerenes are regular hexagons and pentagons. What should we know about these shapes before we start modeling? Here to the left are some measures which all are expressed in terms of the length of edge, A. Primarily, we will need the distances of the edges or corners to the centers of the shape. The angle between two different corners when viewed from the center is 72 degrees in the case of regular pentagons and 60 degrees in the case of regular hexagons. In addition, I found a nice presentation of measures for Fullerenes written by Bernard Nitrost, giving the angle between the normals of two adjacent hexagons as 41.38 degrees and the angle between a hexagon adjacent to a pentagon as 37.38 degrees. After this basic information, let's have a look at the molecule. This is the Fullerene I want to model in this video. In this image, I have used an orthographic camera to be able to really show one complete side of the molecule without any perspective effects. I have rotated the molecule in a position where pentagons are at the very top and at the very bottom of the molecule. According to Bernard Nitrost, the sphere defined by the atoms of the molecule has a radius of 2.48 multiplied by the length of the edges of pentagons and hexagons A. This molecule shows many features of symmetry. One particularly useful feature for modeling is the fact that you can produce the upper half by mirroring the lower half and rotating it by 36 degrees around the y-axis. Therefore, each layer of atoms of the upper half can be produced from a layer of the lower half simply by rotating it around the y-axis by 36 degrees. This facilitates modeling considerably. Now let's start modeling our molecule layer after layer with the bottom pentagon. It is located in the xz plane surrounding the origin. We start at a position at negative x and z values. According to the measures for a regular pentagon recalled above, its coordinates are 0.688 multiplied by a on the x coordinate and minus 0.5 multiplied by a on the z coordinate. By rotating this position 5 times around the y-axis by 72 degrees, we obtain all 5 positions of the pentagon. We will store them as vectors and use them later for positioning spheres and cylinders when it comes to really building up the molecule. Now let's go one layer up. In Fullerenes, each pentagon is surrounded by one row of hexagons, though these will all become hexagons. We start with the position on the y-axis in the distance a, length of the edges for the basic shapes, from the origin. This position is now rotated, first around the x-axis by minus 30 degrees away from us, and second around the z-axis by 90 minus 37.38 degrees, referring to the angle between a hexagon and a pentagon. By shifting this rotated position to position 1, we obtain position 6. And position 6 is then rotated 5 times by 72 degrees around the y-axis to result in positions 7 to 10. Now it's time for layer 3. The positions from layer 3 are in the same plane as the respective positions from layer 2. So we will have to use the same angle for rotating these positions around the z-axis as before. Again, we start with the position on the y-axis, this time in a distance of square root of 3 multiplied by a. This position is then rotated by 90 minus 37.38 degrees around the z-axis and shifted to position 1, resulting in position 11. When we repeat this procedure and shift a new position to position 2, we obtain position 12. For obtaining all the other positions from this layer, we have to rotate both positions 5 times by 72 degrees around the y-axis. Note that we only rotate the positions, not the blue cylinders. When defining cylinders later, we have to be careful to connect the right positions. In this case, position 11 has to be connected to position 6 and position 12 to position 7. For closing the hexagons, we still have to connect positions 11 and 12, 13 and 14, and so on. Layer 3 is finished. Here comes layer 4, which will be our final layer. The rest of the molecule is defined by simple symmetry. For defining positions from layer 4, we start again with a position on the y-axis in the distance a from the origin. This position is then rotated, first around the x-axis by either plus or minus 30 degrees, and then around the z-axis by 90 minus 37.38 minus 41.81 degrees. We are speaking about the positions of a hexagon adjacent to our first hexagon. Therefore, we have to add our first angle to the angle between two adjacent hexagons. These rotated positions are then shifted to position 11 and 12, and here we are at our new positions 21 and 22. These are finally, as in every layer before, rotated 5 times around the y-axis by 72 degrees, and we obtain all positions we need. Connection of positions 22 and 23, 24 and 25, etc. results in closing the current row of pentagons. The rest of the molecule is generated by symmetry operations. Here is layer 5 generated from layer 4. Connection of suitable positions results in hexagons. This is layer 6 generated from layer 3 with suitable connections. Here comes layer 7 generated from layer 2, and finally layer 8 generated from layer 1, and connections for these layers, for this layer. In my Pov-Ray script, which will be available on GitHub soon, I first defined the positions as just shown. I did not use arrays for this point for easing access to my script for beginners. Then I shifted spheres to these positions and finally installed cylinders between them. This last point may be somewhat tricky. When doing this stepwise for each layer, it should work, however. Once you have installed spheres and cylinders, you may transform the structure into a blob, play around with colors, etc. So this time it was a quite complex structure. Next time we will go for something easier, for graphene and graphite. See you then.